Hi, I'm Daniel Chan from UNSW Sydney. This is video 6 in my short course on point set topology. And in this video, I want to talk about a very, very important topological concept called connectedness. Okay, so let's have a look at the basic concept and motivate it with a simple picture where we understand what connected means. Okay, so actually the easier way to approach this notion is to think of the complement, which is disconnectedness. Okay, so here I've got a picture of some subset of R2, and we would all say that it's disconnected. And what's one way to think about how it's disconnected? Well, I guess one way is as follows. It's kind of got two pieces. Okay, so I can separate out the two pieces with a little curve like that. Okay, so on one side of this curve, I guess we have one open set inside R2, and on the other side of the curve, we have another open set. Okay. Now here we're talking about subspaces of R2. If you want to just look at the set itself, okay, and think about that topological space, I guess you can use the Euclidean topology on that, which is the subspace topology. So that means that this piece of this subset of R2, this piece of X is an open set, and this piece of X is an open set. So we see that in this case, this set is a disjoint union of open sets, okay? That's what we have, okay? And those open sets correspond to the two separate pieces of this disconnected set, okay? So that will motivate our definition, which is as follows. Suppose we're just given a topological space X here, okay? When do we say it's disconnected? We'll say it's disconnected if any of these three equivalent conditions hold, okay? So the first one is suggested by this example here. X is going to be the disjoint union of V1 and V2, where V1 and V2 are open sets of X. Okay, so the dot above the union here means that it's disjoint. So V1 intersect V2 is the empty set. Okay, so what does it mean to express X as a disjoint union of two sets V1 and V2? Well, that just means that V2 is the complement of V1, or equivalently, V1 is the complement of V2. Of course, the complement of an open set is a closed set. Okay, so we could just say, well, this is the disjoint union of V2 and V1, and V2 being the complement of V1 is closed, and similarly V1 is closed. So this is actually equivalent to the statement that X is a disjoint union of non-empty closed sets. Okay, so the third equivalent condition, which describes a space being disconnected, is the following. Okay, so we can instead look at just one of them. Okay, the V1. Okay, so the other one, if you have a disjoint union like that, is the complement. And for the complement to be open, it just means that it's closed. So it just means that you can find this V1, which is both open and closed, and to make sure that these two are empty means that this is non-empty, and this V2 being non-empty, I guess means that this one is not the whole space X, okay? So that means that this part, these two conditions here for being disconnected is equivalent to the condition that X has a proper non-empty subset, V1, which is both open and closed. Okay, so proper means that it's not all of X, so that its complement is not empty, and of course you want it to be non-empty as well. Okay, so that's the definition of disconnectedness, and a space which is not disconnected is connected. Okay, so it's defined in this way. So let's just look at a very simple example. Let's look at the set of all non-zero real numbers. Okay, that's our X, non-zero real numbers. It's a subset of the set of real numbers, so it has a Euclidean topology. Of course, you can break it up as to the set of all negative numbers and the set of all positive numbers. They're both open subsets of this X, and since they're disjoint, you've expressed this as a disjoint union of two open subsets, so it is actually disconnected. It's not connected. Okay, so what about some examples of connectedness? Well, it's a little bit harder to show, okay? So what I want to do is I want to actually completely describe connectedness inside the Euclidean, one-dimensional Euclidean space, so just R, okay, the Euclidean line. Okay, and this proposition tells you precisely what those connected sets are. And they're kind of the things that you would imagine, okay? So when is a subset X of R connected? It's connected precisely when it's an interval. So what do I mean by an interval here? I mean things like this closed interval, all the numbers between A and B inclusive, but I also mean things like the open interval, all the things strictly between A and B, not including A and B, and also the half-open interval. So you can have a round bracket on one of them instead of a square bracket, okay? So there are two half-open intervals here as well. So all of those sets are connected, and in fact, these are the only connected subsets of R. And the proofs for both directions are fairly similar, and the more interesting one that I want to show you is to show that an interval is connected, and I'll just do it in this special case here, that the closed interval AB is connected. Okay, so this will at least give you a nice example of some connected spaces. Okay, so let's do that. Okay, let's show that this is connected. Okay, so we want to show it's not disconnected. Okay, so let's write this as a disjoint union V1 and V2 of open sets. Okay, this will be a disjoint union. Okay, so here's our interval from A to B like that. Okay, and we've expressed it, so maybe there's a V1 which we imagine as something like this here. Okay, and without loss of generality, well, A has to be in one of these two sets. Let's make that one V1. Okay, we'll pick V1 to be the one that contains A. So the picture looks like this. Okay, so A is inside here. So V1 is non-empty. Okay, so if V2 can be chosen to be non-empty as well, okay, then of course it's disconnected. So we want to show that actually V2 is the empty set. That's the aim of this proof. Okay, to show that V2 is empty. And this is the way we'll do it. Okay, so we need to use something about the topology of the reals. So you have to have a good understanding of what the reals are first. Okay. What we'll do is we'll look at the following set J. Okay, it's a set of real numbers, and which real numbers are we going to look at? Okay, so we're going to look at intervals A up to X. So which X are we going to look at? We'll have some X maybe here inside this AB, and we'll look at from A to X. And if that interval is contained inside V1, that X is inside J. Okay, so the ones in the picture, well, any X like this, all the way up to here. Okay, they're the elements inside this J pictorial, all the X's, such that that interval from A to X lies inside this V1. Okay, and the key point of the real numbers, so what's special about the real numbers that we're using here is that we know that any bounded set of real numbers has a lowest upper bound. Okay, so this is a property of the reals that needs to be proved depending on how you construct the reals. Okay, so we'll use this property of the real numbers. Okay, so we can talk about C as the lowest upper bound of this J. Okay, so in this picture here, if the V1 looks like this, okay, so what's the largest X such that the interval from A to X lies inside here? If we push X, it can be bigger, bigger, up until here. Okay, that's where the C is. Okay, so that's the C is the lowest upper bound for J. Now, of course, this set is bounded because once you go up to B, right, this V1 is a subset of AB, so you can't go beyond B. So it's a bounded set, and in that case, it's got an upper bound, of course, and so there's a lowest upper bound. Okay, so what does it mean to be a lowest upper bound? Okay, so firstly, it's an upper bound. Okay, so every element in this set is at most C. That's the biggest value that can be in this set is C. But also, if you try to make anything smaller, if you pick a C prime, it's no longer an upper bound. Okay, so if you pick anything C prime strictly less than C, it's not an upper bound. Okay, because this is the lowest of all the upper bounds. Okay, so what does that mean? If C prime here is not an upper bound, that means there's some element X which is bigger than this. Okay, so this doesn't bound it above, so there must be something inside here which is bigger than that. X is greater than C prime with X inside here. And what does it mean for X to be inside here? It means that this interval from A to X is inside V1. Okay, so that's what it means. Okay, so if you look at what's the conclusion from all of this, the takeaway that I want to give you from all of this argument, it's a little bit complicated, it's the following. Okay, firstly, let's look at A up to C prime. Okay, this half open interval from A up to C prime. Okay, since X is greater than C prime, this is contained inside AX, and since that is contained inside V1, this A up to C prime is contained inside V1. Okay, so for any C prime less than, if your C prime is over here, and it's less than this C, then certainly this A up to C prime is inside V1. Okay. Okay, so that's the first thing we note, is that A up to C prime is inside V1. And since this is true for every C prime less than C, that means that in fact the half open interval from A up to C is inside V1. It's contained inside V1. Okay, so let's move on from there. So that's something that we know now. And we want to try to show that V2 is empty. So we're going to look at this point C, and we're going to divide up into two cases. Okay, so what are the two cases? It depends on whether C is inside the set V2 or V1. So remember, this is a partition of this set, so C has to be in one of them. Okay, so let's suppose first that it's inside V2. Okay, so C is inside V2. And remember, these are open sets. This is absolutely critical in the definition of disconnectedness and connectedness. So that means that if it's open, that means that there's some epsilon ball around this C, which is contained inside V2. Okay, so let's put in the epsilon ball here, say it's like this. Okay, so it's an interval like that. Okay, it's inside V2. Now what do you see? So this is inside V2, but remember, A up to C is inside V1, A up to C is inside V1. So this little bit here is an intersection between the two, okay, and that intersection contradicts the fact that these two are disjoint. Okay, so if this interval is inside V2, then there's some actual intersection with V1. V2 contains this, and hence its intersection with V1 is also non-empty, okay, which contradicts what you have here. So we know now that C is not inside V2, so it has to be inside V1. Okay, C is inside V1 now. Okay, so what I want to show in this case here is that actually C will be equal to B. It's not as in this picture here. That's what we want to show. Okay, so let's suppose it's in this picture here, like so. Okay, so now we're going to find some, use the fact that C is inside V1, and similarly V1 is open, so V1 contains some, C rather has an epsilon ball around it, an open neighborhood contained inside V1. Okay, so this is inside V1, A up to C is inside V1, but so is this epsilon ball here, this interval here. So V1 contains this and this, so it contains all the way from A up to the end of this. Okay, so if you look from the half open interval from A up to C plus epsilon, and at least if you intersect that with AB, that's contained inside V1. Okay, but now what happens? Okay, so remember, C was the lowest upper bound of all those x's such that the interval A up to x is in V1. But now you can make x's, those x's inside J go all the way up to C plus epsilon. Those intervals are now inside V1 as well. So C is no longer the lowest upper bound. It's not an upper bound anymore, right? Because you've got some bigger x's inside here. Okay, so that means the only way you can avoid that is if actually C equals B. So the conclusion from that is that C equals B. Okay, so now you have the half open interval A up to B is contained inside V1. And let's look at V2. We want to show that this is the empty set, right? So what's V2? Of course, it's just V1 complement, because this is a disjoint union of the interval. V1 complement, but V1 we said contains this A, C, and C is B. So it's got a half open interval from A, inclusive, all the way up to B, but not necessarily including B. And the complement of that is just a single point at B. The closed interval from B to B is just a single point at B, right? Okay, and the other fact is V2 has to be open. So it's an open subset of just that single point. Okay, so the single point there is not open. Okay, that set is not open. So it has to be the empty set. Okay, so we've shown that if we have a disjoint union like that, okay, one of them we can assume to be non-empty, but once that's non-empty, the other one has to be the empty set. So you can't write this, you can't, so to speak, disconnect the space, this interval, by writing it as a disjoint union of non-empty open sets, and that means that the intervals are connected. Now, connectedness is a topological property. In other words, if you have homeomorphic topological spaces, they are either both connected or they're both disconnected. And the reason for that is because the notion of connectedness is defined just in terms of the topology. Okay, you want to see whether you can write that space as a disjoint union of non-empty open sets. Okay, but actually something stronger is true. Okay, so you don't even need to look at homeomorphisms. Okay, suppose you have a continuous map f from x to y. Okay, and suppose the domain x is connected. Okay, then in that case the image of this f of x is also connected. Okay, so to be connected, of course, you need to talk about the topological space f of x. Now, f of x is a subset of y. This is a topological space. So, of course, we mean it's connected when you think of this topological space with the subspace topology inside Y. Okay, so this of course immediately implies that homeomorphic spaces are, if one of them is connected, then the other one is connected too. Okay, so, but this is actually stronger. Here you just look at a continuous function. And kind of the reason why you expect this to be true is suppose that you have something that's connected. Okay, if you apply a continuous map on that thing, well, continuous kind of means, well, you're allowed to stretch it around a little bit, but you can't break it. So the thing which you find about connected sets is you can't break apart that set so that it becomes disconnected, in the sense that you can express it as a disjoint union of two non-empty open sets. Okay, the proof of this is actually extremely simple, and it's one of the reasons why we set up the language of topology the way it is set up, so that we can quite easily prove theorems which we expect to be true, like this one here. Okay, so let's have a look and see why it's true. So firstly, f goes from x to y. Of course, all the values land inside f of x, so we can restrict the codomain to f of x. Okay, that's a new topological space because it's a new set. Okay, and we give that the subspace topology. And the first thing to note is that this function here is also continuous, and that's quite easy to check why that's true. And of course, it follows from the fact that f itself is continuous and the definition of the subspace topology. Okay, so remember this open sets in here are just the intersections of open sets from here with f of x. Okay, so when you pull back open sets from here, essentially you might as well just pull back from an open set inside here. Okay, so that's a continuous function. Okay, so the way we'll prove this is via the contrapositive. Okay, so what we'll do is we'll assume instead that f of x is disconnected, and we want to show that x is disconnected. Okay, so let's suppose f of x is disconnected. F of x here being disconnected means that it's the disjoint union, say v1 disjoint union v2, of two non-empty open sets v1 and v2. Okay, so you have that there. And now let's have a look at x. Okay, so remember when you look at the inverse image, okay, that preserves unions and intersections. Okay, so the inverse image of this v1 union v2, so let's look at the inverse image of v1 and the inverse image of v2. Its union is of course the inverse image of the whole thing, f of x, which is of course all of x. Okay, so now you've expressed x as a union of two sets, and since these are inverse images of open sets, these are open sets here. Okay, now f inverse also preserves intersections, so since these are disjoint, these inverse images are also the inverse image of the empty set, which means that these two are disjoint as well. So now you've expressed x as a disjoint union of two non-empty open subsets, so that means that x is disconnected. So we've proved the contrapositive of this fact. Okay, so this is a wonderful fact. Okay, you can express it simply as the continuous image of a connected set is connected, and this is something that you'd expect to be true. Okay, so what I want to do now is I want to show you how to prove a theorem that you know already called the intermediate value theorem. This is a theorem that you see in calculus, but I want to show you how it is really topological in nature by just proving it from what we've done already here. Okay, so you expect it to be something that's topological in nature because it's just a theorem that requires continuity. And really, the study of topological spaces is the study of geometry where you're interested in looking at continuous functions between spaces, right, rather than functions with more structure. Okay, so let's just state the intermediate value theorem in the way that we want to prove it. Okay, so we're going to look at a function f, and it goes from the closed interval ab into r. It's a real valued function on this closed interval ab, and we suppose it is continuous. Okay, and the key point is that, well, of course it takes on the value f of a and f of b, but this function f, of course, also takes on every value in between f of a and f of b as well. And now it's very, very easy to come up with a proof of this. Okay, so let me show you how that goes. Okay, so ab is an interval. Okay, closed interval. So this is connected. So we apply f to this ab, so that's the range of this function. Okay, they're the set of values of this f. Okay, this is also going to be connected as well. Okay, you have the image of a connected set is connected. Okay, so what? So this range is going to be some connected subset of R. And I told you in the first proposition what the connected subsets of R are. They are all the intervals. Okay, so they could be half open, open, or closed. So let's suppose it's an interval from C to D, but at the moment we don't know whether it's half open, open, or closed. It will turn out to be closed, but at the moment we don't know. So it's the range of values goes from C to D, but we don't know whether we include C and we don't know whether we include D. Okay. Certainly the range of values includes f of A and f of B. Okay. So we don't know whether f of A is less than or equal to f of B, but we can write them in some order like that. Okay. So the main point is that, well, if you have some interval from say C to D, and inside that interval is both f of A and f of B, then the closed interval between f of A and f of B, that's certainly inside this interval between C and D. And the interval between C and D is a set of the range of this function. So the range of the function certainly includes every value between f of A and f of B. And this reproves the intermediate value theorem just by using these basic results in topology. Okay. So in my next video, I want to have a look at the topological property of path connectedness, which is another way to approach the idea of connectedness.